bimolecular nucleophilic substitution is an SN2 reaction. And it's a very interesting reaction, and the mechanism is fairly straightforward. So let's start off here by taking a look at the mechanism. So we're going to use the nucleophile hydroxide, HO-. So this is our nucleophile. All right. So to this, we're going to add our electrophile. So plus, and I'm going to use a different color here. Let's put our carbon here. So here's our carbon. And let's put a leaving group on here. So the leaving group that I want on here is iodide for right now, okay? And what we have is an H atom, and then let's put on another H, and then our third H right here. So this is our electrophile. And again, to point out here, that iodide is going to be our leaving group. Now, where is the nucleophile going to go? Well, remember, the iodide is pulling a dipole this direction. So it's leaving a delta plus right here. So if you're trying to figure out what's going to be attracted to what, well, the negative thing should be attracted to the positive thing. That makes sense. So this nucleophile, which is our Lewis base, is going to swing over here and do this backside attack, just like this. All right. And when it makes a bond with that, it's going to kick off these electrons, and they're going to come over here to iodide. Now, I don't usually put in transition states here for mechanisms, but I want to show you guys this one here. So hydroxide, HO, right, starting to make a bond here with our carbon atom. And as it does that, these H's, those three H's that we have here, are going to kind of come upright, and they're going to kind of adopt this like planar conformation. So they're going to look like this. Right? And then the bond here is going to start breaking. So this represents our transition state. All right, and then once this is the top of the hill for our activation energy, right? In fact, if we look down below, this is what we just drew. That's our transition state, right? So we're starting off, as far as this is concerned, our hydroxide down here, right? Here's our methyl iodide, and we've just come up to this point right here. And once we're at the top of that hill, then we're really just going to lose the iodide. And we're going to make a bond, a full bond, right, to our hydroxide. But look what's happened here. Our HO is going to come over, and it's going to make a bond to this carbon. Now the H's that are kind of sitting upright right here, they're not going to come back and do some weird kind of, angle like this, right? They're going to keep moving that direction because of VSEPR essentially. So we're going to move this way, and that way. So what's going to happen here is we're going to have our H come up just like so, another H down here, and then an H back just like this. Right, so this is our product. And then the other thing that we get here is we get iodide, so I minus. That is our leaving group. For the sake of writing out reactions, we often omit iodide and we just include the organic product here. Now if we look down below here at the reaction energy profile, we already saw half of it, right? We started here and we came up to this point right up here. And now what we're going to do is we're going to swing down here and we become our product, right? And then there's your iodide. And then this energy difference right here would be your delta H, right, for the overall reaction. And then remember that this peak right here, this hill, right, remember guys, that's your activation energy. This reaction right now is an exothermic reaction. And our transition state for an exothermic reaction looks more like the reactants than it does our products here. And recall that's a consequence of something called the Hammond postulate. Now there's some interesting stereochemical, results that occur from this reaction. And this is something that really needs to be pointed out. This reaction only occurs if the reactant, right, our nucleophile, and the other reactant, the electrophile, they have to hit each other in the correct orientation. So they have to do so with the right orientation and with a sufficient amount of energy to overcome that activation energy. Now, the rate law for this, again, something experimentally determined, but it's equal to the concentration of the substrate times the concentration in the nucleophile. So both of these are going to affect your reaction rate. So it's SN2 is second order overall, right? Remember, the sum of our exponents is what we do to figure out what our rate law is, right? So again, an increase in nucleophile concentration increases reaction rate here. And that's why we get a 2. So this is substitution, nucleophilic, bimolecular. Now let's take a look at the stereochemistry of this SN2 reaction. It has some interesting stereochemical consequences. And let's start off here with a different nucleophile. So I'm going to use here CH3O-. So this is going to be, this is methoxide. It's our nucleophile. It's our Lewis base. And again, the name of this thing is methoxide. All right, and then what's going to happen here is that this is going to come over and react with our electrophile. And our electrophile here, we're going to write out this as a carbon. I want to put an iodo group here. Then we're going to put a CH3 here. And then we need to have groups on as a wedge and a dash. So that's our hydrogen. And then at this position, I want to put CH2CH3. Now, let's take a second. Let's go back to what we learned in stereochemistry. And let's determine whether or not this is R or if this is S. So as far as numbering these things, this would be number 1. This would be number 4. This side would be number 2. And then up here would be number 3. So that's moving around this direction, and that makes this an R right now. Okay? So what's going to happen then is this methoxide needs to come over here, and it needs to hit. And it hits the backside of this carbon. Right? It turns out that it's one of the anti-bonding orbitals of carbon, and we don't get into an orbital description of the SN2 reaction. It's just too much for, in many cases, at this level. But it's something that's interesting if you go on. So carbon and oxygen make a bond, and then bam, we kick off iodide. All right, guys, so let's skip that transition state and let's draw out what our product is here. So we get CH3O, and then we're going to be bonded now to our carbon. So that carbon is here. And remember, what we saw before was that CH3, that H here, and then this ethyl group, they're all going to move that direction. It's kind of like, I always thought of this like an umbrella kind of getting caught in the wind and getting like flipped out or inverted a little. So that's going to put our CH3 here. It's going to put our ethyl group here and our H group right here. All right. And then, of course, we're going to get plus I minus. Now, what we call this here is inversion. So there's two things that are important. This attack that occurs right here is called a backside attack. All right. And then what happened here at this carbon right here, we call inversion. So that's when that umbrella like flips backwards, essentially. Now if we look at this and label this as RRS, let's do it. So this would be number 1, this would be 2, that's 4, and this is 3. So it goes this direction right now. H is pointing away from us, and right now that is S. Now, there's 2 really important points here with this. The first one is that inversion, okay, it doesn't mean that S converts to R, right? Or in this case, R goes to S. Often this happens, but it depends on the priorities of our nucleophile and our leaving group. So we can do experiments in which this does not occur. And the second thing is that inversion does not affect other chiral centers in the substrate. It only affects the carbon that has chirality in it, right? So only the reacting carbon would be inverted. If you have a really long molecule and at carbon number 2, the reaction is taking place. At carbon number 16, nothing is happening then, right? So let's look at 2 examples here down below and see if we can kind of put this together before we move on. All right, so the first one that I want to look at with you guys is this. And we don't tend to draw reactions out like I drew up above because we don't want to have to redraw all these zigzag forms. So what we typically see is something like this. So here's our iodo group, right? We go through here and we would use like sodium hydroxide, so Na plus, O minus, right? And we would carry out this reaction. So when we look at this, by the way, this is a secondary alkyl halide. So we need to be aware of that, right? So secondary means that that group right here that's connected to our iodine has 2 R groups on it, right? It's got the methyl on one side and it's got the ethyl on the other side, so it gives you a secondary. The other thing is that at this position we have here an H atom that's there. Right now, the hydroxide needs to swing around here and react at this carbon. And when it does that, it's going to take this H and it's going to push it into this forward position, right? Because it actually needs to tack 180 degrees away from our iodo group. So it's kind of going like if you can just put your hand behind your computer, that's where it's going to be reacting in that angle. So then what we're going to get as our product is this. So our H group now has been inverted. That's showing the inversion there. So we don't have to put the H there. I like to put it in there though because it kind of reminds me as to what happened as far as the inversion. So there's our H, and then our OH would be hanging out here in the back. Okay, so again, that's kind of the process of how we would see that inversion under normal kind of, bond-lined formula type situations. So what we're going to do is we're going to analyze this. This is a secondary alkyl halide, and then we take a look down here, and let's talk about hydroxide. So hydroxide is a strong base, and most often strong bases turn out to be strong nucleophiles. And there's a whole list of these things where you might have strong bases not be good nucleophiles or strong nucleophiles be weak bases. And we'll get into that as we kind of assimilate more information. All right, now let's do another example here too. So let's do one more here. So what I'm going to do is I'm going to look at this one with you guys. So let's come over here and let's do this. And let's put that carbon number 2 here. Let's put a bromo group. So here's a bromo group. And then I'm going to put in the H just to help us kind of keep track of what's happening here. All right, now I want to react this with cyanide. So we're going to take this and we're going to add NaCN. What that is Na plus and Cn minus. Okay. Now let's take a look at this and let's see if we can draw out what our reaction would be. So let's go through. Cyanide's coming around. It's doing that same thing. This is the carbon that we're attacking right here. right? And then we're kicking off bromide right here, right? So just like before, we see that same type of flow, right? So before, hydroxide came over and made this bond, right? And then we got to put that arrow in. We would lose, in this case, right, just like we did on that previous page, we would lose our iodide, right? So we want to make sure we put that in, right? So then coming back over here, looking at this, let's draw what our product is. So our product is 1, 2, 3, same backbone there, except now that H is going to swing around in the front. So there's your H atom, and then back here, carbon triple bonded nitrogen. All right, and then let's play around here and let's figure out R and S for this one, just for fun. So looking at this first structure here, the bromo group's number 1, H is number 4, this side's number 2, that side's number 3. So we're moving around this direction. H is pointing away from us. That is the R direction. All right, now let's take a look at our product. Let's go through and figure out what this one's going to be. So let's see. So number 4 is easy. That's going to be number 4. Looking at this, this is probably going to be number 3. So we have to now figure out who number 1 and number 2 is. So at this first point of attachment right here, right, those are both, let's do this, it's a carbon atom, and over here you have a carbon atom. So there's a tie right off the bat. All right, so then we move down the line, right? So when we move down the line, that carbon is connected to a nitrogen, a nitrogen, and a nitrogen. It's a triple bond. Remember, we have to count it 3 times then, right? It's the actual nitrogen and then these 2 phantom nitrogens, essentially. Now, if we move down the line with this carbon, that carbon right there is connected to an oxygen, and then a hydrogen, and a hydrogen. So what has the higher atomic number? Oxygen does. So that makes this side number 1, and it makes this guy over here number 2. Right, so we're going here from a 1 to a 2 to a 3. It's moving around this direction. Okay, so then it's S. Well, then did we go from R to S? Well, in this case, not really, right? Because remember, number 4, our lowest priority, is pointing towards us. So recall, we have to switch our answer to R. So here's an example, and I like to throw this one out there. Here's an example of where we have inversion, but we didn't interchange our stereochemistry, and R remained in R. And again, I just chose this problem just to illustrate the point that inversion does not mean necessarily that S converts to R or vice versa. So just kind of be wary of that as you go through these problems.